Hello, good to see you, Bethany.
Hi, I'm
Come on, grab a
Bethany.
seat. Hey, Robert, glad to have you here.
Robert.
Well, I'm glad to have you guys here today. I'm going to talk to you uh, about an action research project that I've done with my chemistry class. So the question that my action research covered was, will the implementation of an active learning model in a high school chemistry class improve my students' conceptual understanding? Now, I am in a large high school in mid Missouri. We have about 2,500 students. Um, the student population for my study is about 148 students, and they're mostly 11th graders and some 12th graders in a general chemistry class. The original impetus for the study is my noticing students' ability to follow a pattern or answer a mathematical operation question, but if pushed a little further on understanding the underlying concepts, they were not able to do that. And what I've seen in subsequent chemistry classes with my students is the students who have a conceptual understanding are better able to apply that knowledge to a new content area. Here, I'm looking at how implementing an active learning model will impact my high school students' ability to improve their conceptual understanding of some chemistry ideas. The active learning model that I'm using is connected with the POGLE, process-oriented inquiry guided learning model system. And this is a system that provides students with models of situations or systems and is designed for them to discover the understanding of that concept, to deepen, to refine, to integrate that knowledge into this new discipline, this new content that they're learning. In working with my students, I noticed students who are able to correctly answer problems, but not express the underlying causes or the underlying reason for the either chemical behavior or chemical property. They could easily memorize a pattern that as we go across the table, the size of the atoms gets smaller, but not explain why. Um, in this graph, I had given the students a short conceptual quiz and was just looking to see how many people were able to articulate the why. And we see the data here, with only about 35% of the students actually having the correct answer and the correct explanation for that answer, the reason why. In support of using the POGLE model, I found a few research studies. Freeman et al. 2014 showed that using an active learning model reduced the failure rate for students in the course, as well as boosting exam scores. And a study by Hine 2012, in a 2012 research, Hine showed an ability for an active learning model to overcome student learning gaps. So students who had missed some content or hadn't had specific experiences were able to gain some conceptual understanding and overcome that gap. This initial conceptual understanding was measured through the use of formative quizzes, selected items on unit exams, and individual conferences with students. Within the conferences, I was focusing on their causational explanations for chemical phenomena and properties. Additionally, I used student exam scores from Unit 2 exam and Unit 3 exam. The Unit 2 exam had occurred just prior to the implementation of some of these POGIL methods. And though they're two different units, I wanted to look at the proportion of students coming across the success line. So reducing my number of failing students and moving more students into that AB range. So in collecting the data from students Unit 2 exam and Unit 3 exam, both I collected the data in an Excel spreadsheet and broke it out into essentially a histogram of different grades, F, D minus, D, D plus, C minus, and so on. And as you can see, in our initial Unit 2 exam prior to this implementation, we have large number of students in the A range, some students going through that mid range, and then at the end, a large number of students who did not make a passing grade. So that, in this case, 21 out of 148 students with a F grade, below 60% grade. And even in the other groups, I also look here at students below C, which was about 27%, and students below a B and below are 38.5%. Now, those last two categories, below a C and below a B minus, by the time we got to the Unit 3 exam, had improved a little bit. We went from 27% below a C to 24%, so 3% roughly moved up there or moved out of that category. And in the below a B minus range, from 38.5% to 35.8%. So again, there we have about a 3% change. The part that I was most excited about and most happy about is our percentage of students who had gotten below a 60. And again, that was 21 out of 148 students on the first exam. On Unit 3 exam, the second exam, uh, it's out of 137 students. Some students had not taken the exam yet or were not in that sample. But as you can see, the number of Fs is down to one. So one in 137 students. That is what, about 0.7%. So a huge improvement there. Um, Overall, it's not a big move. In fact, it looks like a lot more Bs, a lot more A minuses. So more students moving up. Um, but again, I'm most happy about pulling my students who were not at least at the passing mark into that passing mark. On further implementation of this research, something I would like to see is a more longitudinal study in this area. How are the students continuing to gain conceptual knowledge through the use of these active learning models? And more importantly, what does that do for them as they go to the next class? So as you move from this chemistry to another science class, are they able to take that conceptual knowledge and transfer it to new information? Um, the other thing I saw in my study that going forward or doing this again, I would like to add in is looking at some of the academic background differences in the students coming into the study. Even though these students are all in the general chemistry on level chemistry class, um, when I go through my group of students, I have students in geometry math level and all the way through AP Calc BC math level, all within the same class. We have 7 different levels of math, and students are there from geometry, algebra, college algebra, statistics, and in the AP Calc classes. When I look at the grades, of course, the students who are in the AP Calc classes are also doing well in the chemistry class, but I think maybe breaking the groups out might give us a little more information of the efficacy of this model. And then a final question that came up for me was, would this increased conceptual understanding, this ability to think about the why, cause students to be more interested in science and want to continue their science education or their science careers? So let me hear if you guys have any questions. What do you think of this? Would you like me to explain something further? Yes, Miss Mosley.
I have two questions. My first question is about student buy-in. Did you notice the students engage in your conferencing? And um, were they active participants?
Indeed. I think yes on two points there. In terms of the student buy-in, most of the activities, the things that are in this are group activities. So you're working with your pod, maybe three people, maybe four people, and they're novel for the students. So when they get it, it's a new picture, it's a new model, it's a new description. And I've had to work with them to untrain what they've learned of rush to the question and try to answer the paper, but stop, work on the model, understand the model, then the questions are easy. And they have bought in and they do seem to be doing that.
My second question is about teaching overall. I'm also a teacher.
Mhm.
And as a teacher, we're always kind of searching for a student to have that light bulb moment or that aha moment. Do you have any, I don't know, anecdotal stories about how this relates to a student really grasping a concept and ingraining it in their um, ingraining it in their learning
Sure, absolutely. Um, Actually, I think I have one specific anecdotal one, which was just a few days ago, and kind of a general feel and what's been happening. But um, one of my roles at school is also I work in the science tutoring office also, and I had a student from a different chemistry course, not the general chem, but not the chem that we were doing, but a different class, who had come in for some help with some chemistry work and some concepts, and I didn't really work with him explaining those specific concepts, but we worked with explaining why those things were happening. And by the end of maybe 30 minutes with him in the tutoring center, he was just like, "Oh, well, that makes so much more sense now. It makes a lot more sense if you know why." So, for specific anecdotal one there. And then in general, I know in my classroom with the students that I work with, when they're able to understand why, they're much more capable when it comes to, okay, we're going to make this a little bit harder, or we're going to transfer it to a new area, to a new topic, but it's not a completely new topic. It's still connected, and they can see the connection and say, oh, well, this is what happened here, so maybe this is what's going to happen here. So yeah, I've definitely seen that. But again, like I said earlier, this is a very narrow study in a very short period of time. So I'd like to see more.
very good.
So thank you guys.